gensets are the key backup application asset that's ready on standby to provide power in the case the grid goes out. And so this was a first look at whether such a system as is shown here today can power a data center. This is a project overview and background. And this is a 3-year project that we've received financial assistance from the DOE. And this is to demonstrate a 1.5 megawatt hydrogen fuel data center backup power application. The picture on the left here, there's mainly 3 color codings, and we'll start with the blue part. We're looking at everything all the way from hydrogen production to processing, in this case, liquefaction, delivery, hydrogen infrastructure on site. And the fuel cell takes gaseous hydrogen, and so this involves converting or vaporizing the liquid hydrogen into a gaseous form that the fuel cell can take. And as mentioned earlier, this is a first of kind, never been done before, megawatt scale fuel cell that's been demonstrated at a data center. And this solution is more than just a backup power application. What Caterpillar brought to the table in terms of innovation is controls and systems architecture. We're able to flow power from many different assets in multiple directions. We can use the hydrogen molecules to charge our batteries, or we can charge our batteries from the grid, and we can flow power to the data center or even back to the grid to support the grid. So that's our project in a nutshell. In terms of impact and relevance, this is a famous hydrogen at scale slide that you see at many meetings, basically speaking to the fact that hydrogen today is mainly used in ammonia production or for refining, but the vision here is can we use excess energy to create an energy buffer in the form of hydrogen and then use it for power generation, either for backup power or continuous or some form in between. And so with the DOE goals that we're looking at, again, this office that we're involved in, we're looking at systems development and integration. We're assessing the commercial readiness of such a system and what the greenhouse gas impacts are. So this is what the site looks like. The size of this site here and what you see in the picture, it's about the size of a football field. And if we start on the bottom right with the liquid hydrogen tank, we're looking at a 18,000 gallon tank that then sends the fuel to the 2 vaporizers in the back, and it comes along a gas train and a pipe that runs up that interface between the road and the concrete pad, and then up and over to the Ballard fuel cell. Around the Ballard fuel cell, you'd see the balance of plant, and you can quite clearly see the cooling package to the right of this picture, and the inverter to turn DC power into AC power, transformer, and the switchgear. And in terms of the Caterpillar assets or the CAT batteries, we have the 2 energy storage systems to the top left of this picture, ESS 1 and 2. And the fuel cell recycles most of the water, but this demonstration took place in Cheyenne in a really dry environment. And to get to the right humidity levels in the stacks, we do have DI water tanks. And for those of you with really sharp eyes, you would notice that there's insulation along the DI water tanks and a pipe. Cheyenne wasn't the first place or the original location that we were going to do this demonstration at, but with the business conditions and plans that Microsoft had, this was a site that we were assigned to, and yeah, it made for a really challenging place to do a demonstration because one, this is at altitude, so we're above 6,000 feet. It's a challenge for air systems in terms of getting the right pressure ratio and the right amount of air to your fuel cell stacks, and really cold conditions. This took place in the fall, but first snowfall in the Cheyenne, Wyoming area is mid October, and yeah, we did have some days when we were running under below freezing conditions, and just really challenging. But yeah, all of the equipment that you see here held up, and yeah, we were able to uh, do all of our tests successfully. And I I would maybe say this presentation is a teaser for a future presentation to come, given the amount of reviews that we have to do. But we did a battery of testing here. We've done load steps, load both up and down. We've tested a 48-hour run and many long endurance hour runs. And to our knowledge, this has never been done before on a megawatt type scale. We've run countless tests over 4 hours, over 8 hours, 16 hours, 24 hours, and that headline number that you saw, a 48-hour test. But there'll be more data coming out once we get the right releases, and so yeah, keep your eyes tuned on that. In terms of safety, we at Caterpillar, this is one of our goals, safety first, and we want to maintain a safe work site. And this is for anyone that comes to this site that you saw in the previous slide, whether it's a Caterpillar person such as myself, or a contractor or a sub of a contractor. Everyone that comes to the site goes through hydrogen training, is made aware of the safety aspects of this installation with the cryogenic aspect of it, as well as the gaseous aspect of hydrogen. And a lot of work was put into making this happen from the get-go. We worked in the hydrogen safety plan. We had involvement from the hydrogen safety panel with our partner NREL and Caterpillar's own hydrogen infrastructure expert. Yeah, a lot of people put a lot of person hours to create many plans and partake in many safety activities to come up with the safe design that was then permitted, approved, and when we got to the site, there's additional training for anyone and everyone that would step in there and to have a safe work environment. And very proud to say that we've not had we had 0 incidents. So very proud of that fact, and that this was done in a safe manner. In terms of collaboration, coordination, Caterpillar was a prime awardee for this project, and so we're the lead responsible for the overall project requirements, systems integration, controls development, installation, and demonstration. As mentioned earlier, Microsoft is a non-funded participant, but they were the host of the demonstration site and provided a lot of support in terms of actually making this happen. And yeah, it's quite a big feat to actually have this take place in a live data center environment. There's many considerations that go into that. And you will hear from Ballard here in a bit. He's going to talk some more about large format fuel cells and stationary power. As mentioned earlier, NREL, they were one of the participants here that helped with hydrogen safety, techno-economic analysis, and greenhouse gas impacts. The next 2 slides are actually work that was produced by NREL as part of this project, and I'm going to speak to them in a few. McKinsey was the engineering, procurement, and construction firm that was involved with the design, layout, and site preparation, installation, and they stayed on site for any help with any fixes that needed to be done while we were running, and then decommissioning. So here's the first of two slides from NREL. This is the techno-economic analysis, and this was done at the early stage of this project when we were looking at requirements and whether this would play. We've got a few different systems that are being considered here. We've got batteries, we've got a traditional diesel genset, and a few different flavors of fuel cells, custom or purpose-built stationary fuel cell versus a fuel cell that's being cobbled up by heavy-duty fuel cells, and then two types of hydrogen storage, one being gaseous and the other being liquid. The key thing to take away from this chart, well, the first thing that sticks out is that super big bar, and that's batteries. And to be able to power a data center for up to 48 hours in the event of grid loss, that's a lot of batteries and a lot of costs. And so that's pretty prohibitive. Anytime you need power more than, say, maybe 9, 10, 11, or 12 hours, you're looking at a different energy vector. And so diesel's really good because of the power density that's found there. And there's hydrogen's less dense, but we see, one of the takeaways from this slide is that, in a future state where there's a lot of production or the volumes go up for fuel cells, there's some line of sight to approaching parity with the diesel genset. This is the second slide from NREL. This is on the greenhouse gas emissions analysis, and we looked at a variety of different things here. And again, the diesel genset's the baseline here, and we've got many different bars over here, just looking at a variety of different prime movers. We've got a traditional diesel genset with biodiesel. We've got a spark-ignited genset that's running on natural gas. We also looked at off-site solar for producing hydrogen and on-site solar, and also looked at a grid mix. This is by no means all encompassing, but for this study, we looked at the grid in Wyoming. We looked at the grid in Washington State and the grid in Virginia, where there's a bunch of data centers, and we did consider steam methane reforming as well, and a bunch of different technologies. But one of the key things that sticks out here is that on-site hydrogen generation would probably be one of the ones that would come out as the lowest form of carbon emissions. In terms of gaps and barriers to adoption, this was a big thing and one that we faced while doing this demonstration: hydrogen cost and availability. The other aspect is the power density of a fuel cell. Here we've got a 40-foot container that's 1.5 megawatts. And you look across the street, you've got another 40-foot container that's got a diesel genset that's twice the power. First costs of fuel cells and systems and space requirements with cooling, setback distances, and other subsystems. None of this should come off as a surprise, and the DOE and many other people in the industry are working to address each one of the bullets here. But this is what we see currently in terms of gaps and barriers to adoption. And with that, I will finish off with the final slide. Very happy to say we've got a successful and very safe demonstration showing this hydrogen backup power at a data center. the fuel cell plus battery microgrid solution provides applicability beyond just a standby. So yes, it can perform as a diesel genset standby replacement, but it can do more than that. It can be working in an islanded mode or be connected to the grid, provide firming or provide other modes of function. And just finish off, what this solution brings is increased resiliency, a lower carbon intensity solution, and an integrated system. So I will finish with that, and I'll pass it back to you, Pete.
Okay, great. Thanks, Paul. Wonderful. Now we're going to hear from Patrick Savoy from Ballard Systems, and he's going to talk about some particulars about the fuel cell itself. So Patrick, yours. Thank you.
Okay. I'll take the screen. Can everyone hear me okay?
You're a little faint. If you can get closer to the microphone, maybe, Patrick, that would be good.
Okay, I'll step closer. All right, well, thank you everyone for joining this on a hopefully beautiful sunny day, Friday afternoon at least. That's what it looks like for me here in Montreal. My name is Patrick Savoy. I'm leading the business development effort for stationary application fuel cells in North America. Thank you, Paul. First I want to start by saying we wouldn't have been able to do this, of course, without Caterpillar. Fantastic partner in this adventure for, as Paul mentioned, the first large megawatt PEM fuel cell installed in the USA. So as everyone probably knows who Caterpillar is, I figured I'd take at least 30 seconds to introduce Ballard. Perhaps some of you don't know who we are. So Ballard is a 44-year-old startup based in Vancouver, so that's Pacific side of Canada. Essentially, for the better part of the company's life, we've been making fuel cells. And so we've gotten good at it to the point now where we are really scaling up and increasing production as the market demand is increasing as well. Really, we're at an influx point, I think, with a lot of the announcement policies in place for hydrogen and fuel cells around the world. So very quickly, we touch on 5 different verticals. So the bus segment is probably the one that's the most mature. Truck is definitely second. We've got some trains, locomotives, projects. In the maritime sector, the Scandinavian countries have a lot of policy to decarbonize a lot of the marine ships. And so we're seeing a lot of market pull there. And then finally, for the purpose of this presentation, on the stationary side, we've accumulated up to 8 megawatts of installed products. So quite proud of that. So what is the Ballard brand? Well, first of all, with regards to stationary, we definitely want to show that it's a proven technology. And I think the presentation with Caterpillar and a few other projects, we've proven that stationary has a place. There are, some use cases that have, maybe opportunities for different types of technologies, but there's definitely a space where fuel cells can make a difference in decarbonizing our world. The performance of these, 99.9 reliable, 50% is the average efficiency. So that's energy in, energy out. And of course, byproducts for PEM fuel cells is essentially water or steam, as you saw in the picture, and heat. And finally, we are a company that goes right to the end. We want to make sure that our customers have a good experience with Ballard because it's still a market that is growing, and you need to show that you're going to stand behind your products. Otherwise, they will flick back to traditional means of generating power. So we really stand behind our customers when it comes to supporting them in the fuel cell adventure and journey. A lot of times I'm asked when we talk about fuel cell for stationary applications to touch a little bit on solid oxide fuel cell versus PEM fuel cells. So let me try to maybe summarize that for you. The PEM, so proton exchange membrane, is what Ballard manufactures, and solid oxide fuel cells are different in nature. It is a fuel cell, but they do operate at a much higher temperature, and they can actually utilize different fuels, whereas a PEM fuel cell requires pure hydrogen. So I'm not going to read through the table here. I think these presentations are going to be shared afterwards, but it gives you sort of a high level of where it makes sense to go with the PEM and where it makes sense to perhaps go with solid oxide. And I think maybe the key takeaways are the four sort of symbols or bullet points at the top of the screen. So the PEM fuel cell can load follow, meaning that as the load fluctuates, the PEM fuel cell can adapt quickly and has a ramp up or ramp down rate that is much faster than a solid oxide fuel cell, which typically would be used more as a base load type of production. PEM is a proven technology. Yeah, well, 44 years in, of course, technology always improves, and we can always make it more efficient and more compact. Certainly, some of the challenges that we're trying to address, as Paul mentioned in the latter part of his presentation. PEM is a truly zero emissions technology. I think that's probably one of the major differentiators between solid oxide and PEM, is that, as I said, the byproduct is, well, of course, electricity, heat, and water. Whereas solid oxide, better than diesel, better than natural gas, but there is still combustion where you will have a release of NOx and SOx. And finally, to touch on a little bit of the lessons learned and, what is the hurdles or the challenges, it's the cost. Of course, today, a PEM fuel cell is more expensive than your traditional natural gas or diesel engine. However, most of the production, the forecasted vision that we see in the marketplace, not just Ballard, but through consultants, through our competitors, scaling up is going to mean there will be more sub-suppliers, there will be more volume, and it's all about volume and scale. And so we firmly believe that by 2030, a PEM engine, if you want, or a PEM fuel cell should be cost comparable to a diesel engine. So food for thought. And speaking of food, I like this slide just to put a bit of humor into sort of high technology and highly technical equipment. We always operate with a battery. So you saw it in Paul's slide where there was ESS1 and ESS2. And the reason for this is that although a PEM fuel cell has a fast ramp up, ramp down, it won't match the instantaneous power or current delivery that a battery can do. So in most applications, whether it's onboard vehicles, the buses, the trucks, the ships, and in stationary, we do work with a battery as well. So the battery is there essentially for those short spurts of energy, instantaneous, and that would be the jelly in your peanut butter and jelly sandwich, whereas the fuel cell is more of the long-term energy storage where you will supply a steady state of power as long as you've got the reservoir and the hydrogen available to you. So quickly, just how do we address the stationary market? We've got modular stepping blocks, if you want, 200 kilowatts to the left side of your screen. Looks like a switchgear. You can parallel as many as 6 together with a single PLC controller. You can go to a 2, 3, 4 type applications for anything under a megawatt. And then to the right-hand side, well, it sort of looks similar to what we did with Caterpillar, which is a containerized version for fuel cells. So essentially, all the takeaway here is that for whatever the power needs that you have for stationary applications, we can meet them. I would say at a minimum 200 kilowatts and above. So the project that Paul mentioned, of course, so these are some of the pictures that were taken from that site as well. And I thought I'd just kind of delineate a little bit what was the Ballard scope and what was the Caterpillar scope. So in this case, we had the fuel cell scope, of course, so that's the container that you see top of your screen, which is a true output of 1.5 megawatts, because the actual fuel cell powers our internal equipment. So the compressors, the pumps, your HRB, all of that is powered via the fuel cell. So in fact, the real, I would say, nominal output of the fuel cell is roughly around 1.8 megawatts. We did include the cooling pump skid, so that would be the sort of circulation pumps for the liquid cooling, and also the heat management. If you would need to reach higher megawatt capabilities, of course, you can just take as many of these containers to reach whatever megawatt load that you have. And just to maybe focus a little bit on the technology provided by Ballard, because this is really where the secret ingredients to the recipe lies, is in with the stacks. So the bottom right-hand side picture, you can see sort of the red pipes. These are all the strings of stacks that are placed inside the container. So if you look to the picture above, you see that there are some panels there. And in the picture to the bottom of the screen, you can see the panels have been removed, so you can actually see the fuel cell stacks. And I just put a picture there so that you can see up close what is a fuel cell stack. So altogether, to reach 1.5 megawatts, we have 11 strings of 6 stacks per string, and which each stack is approximately 50 kilowatts. All right, so what are the applications for stationary? Maybe the one slide that you need to remember. So for what we see, at least in the marketplace today, 4 applications that come up regularly. One is EV chargers, because the grid is constrained, so I'll explain that a little bit further. Shore power, so in the ports when the vessels are coming in and they're at berth, they turn off their propulsion engines, but they need to maintain hotel loads. Number 3, data center, of course, that's really what we've been talking about. And number 4, I think Paul mentioned that a little bit as well. So in sort of a microgrid application, where you have essentially a fuel cell to operate as a diesel genset in combination or in tandem with solar power, batteries, and wind. And so maybe just quickly, the picture at the bottom right-hand side of this screen, you see that there's a highlight out of French Guiana. So one of our channel partners has developed a project there, which is overseen by Siemens Energy. And it's a 3 megawatt fuel cell with 55 megawatts of solar, 16 megawatts electrolyzer, 88 megawatt hour of hydrogen capability or of storage, and 40 megawatt hour battery. So that's a project that's ongoing and should come to term, I would say, by the end of this year. So another great application for fuel cells in terms of a microgrid environment. So just diving deeper into these 4 use cases. So a lot of times the fleet owners have they want to decarbonize, they want to bring in EV vehicles, and then you try to get 10, 20, 30 chargers. Think of a UPS or think of a Walmart distribution center of some kind. And in some areas of the country, the grid is constrained. There's not enough current available to plug all of these vehicles. So it would kind of be, if you were to run a diesel genset to electrify your EV fleet, that would be kind of counterproductive. So a fuel cell can be used for those times or those areas where the grid is constrained, or perhaps it's going to take too long. Sometimes it's all about the wait time to get that permission to connect all of these EV chargers. So we're there with a fuel cell solution for level 1, 2, 3 chargers. Shore power. So touched on that a little bit. We also see where shore power can become really a hub in the sense that if you've got the need or the requirement for hotel load power, then you have to bring in fuel cell and hydrogen storage. So having hydrogen storage there would mean that perhaps you could also look to drayage trucks or any kind of port operation vehicles to utilize that hydrogen that's available on site. So we see that as being really a good use case where you could bring in hydrogen, whether it's gaseous or liquefied, and have sort of a little microenvironment of trucks and other port equipment, and of course stationary to power the ships when they're at dock. So maybe data centers, we've talked a lot about it, but there's a huge uptake in data center requirements. I've spoken to many large data center operators, and the fear is AI, which is really eating up a lot of bandwidth and data. And so they rapidly need to increase their capabilities. And again, it's all about having that redundancy when it comes to data centers. So of course, a diesel genset is great, but if you're thinking of more in the catastrophe type scenarios where 4 hours of battery is not sufficient, I think Paul mentioned that in his presentation. If you're thinking about 12 hours, 24 hours, and beyond, 2, 3, 4 days, you definitely need to have something other than batteries. And so this is where fuel cell, zero emission, zero pollution can come in. And finally, well, we talked a little bit about the microgrid environment, but maybe I want to touch on also another use case of peak shaving. Again, in certain instances and jurisdictions, peak shaving, the requirements there are perhaps 2 hours, peak hour, daytime, middle of the afternoon when all the air conditioners are turned on. But in other jurisdictions, the peaker plants, so natural gas peaker plants, are providing more like 4 or 5 days of power because there's a big, cold vortex of some kind or a heat wave in the southern part of the USA. And so a lot of questions around the possibility of using fuel cells as a peaker plant is also, I think, with this project, a testimony that we can meet these types of sporadic events in terms of peak shaving. So altogether, it gives you a sort of a broad perspective of what is stationary and applications where fuel cells make sense. I want to say thank you for your attention, and I'll pass it over to Pete if there are any questions from the audience.
Great. Thank you, Patrick. Really appreciate it. We have many questions. I'm not sure we're going to get to them all, but we're going to try to answer as many as we can. So the first one is, what's the maximum electrical load at the data center? Specifically what capacity is the fuel cell system replacing? Paul, you want to try that one?
Yeah, so this fuel cell is rated at 1.5 megawatt. AC out. And from current data center designs and white papers from Microsoft, we look at maybe 75% load usage. And so during that 48-hour run, we ran at about 1.25 megawatts continuously.
Yeah. So I'm going to combine these next two, the cost of hydrogen and also the cost of electricity out of the fuel cell to the data center. You want to take that one, Paul?
Yeah, this is from that NREL slide, I'm guessing.
Yeah, probably so.
Yeah, based on the work we did there and the assumptions we use, for a diesel genset, we're looking at say 58 cents per kilowatt hour, and this is 2021 dollar numbers. For the best case, for the heavy duty fuel cell and liquid hydrogen storage, in this case, we had about 77 cents per kilowatt hour.
Okay. Next one's for me, really. Any grants and funding available to offset the costs, implementation costs? I urge you to take a look at the DOE Loan Program Office for opportunities there. I don't know of any grants or funding available currently, open solicitations for this kind of application right now, but they could be out there. I just don't know of any. Okay, so the cost of this system versus the cost of a traditional generator, just percentage or 2x, 3x, whatever you want to, however you want to answer that, Paul.
So it depends on how you draw the boundary
Yeah,
of the system, right? If you just say, 1-to-1, 40-foot container to 40-foot container and just fuel cell versus diesel genset, maybe roughly, okay, maybe 1.5x, maybe, but we're not really, we're bringing to the table a lot more than just, a fuel cell by itself. And as Patrick mentioned, it's, the fuel cell and the batteries, they often go hand in hand, whether it's for mobile power or stationary. And so there's more capabilities to what we brought to the table here. So and that cost would go up. So it's then it's no longer 1.5x, but
yeah,
2 to 3x. So
sure. Okay, so here's a kind of a long question. It'd have to be a long answer, but what are the thoughts on small to medium-sized manufacturing sites wanting to use hydrogen to power their work sites? I would say see Patrick separately, if that's okay,
yeah,
because that's just a little bit too broad for this venue. But Patrick would be happy to answer that, right, Patrick? Um, what's the percentage of power that was provided? Basically, did this system provide all the power needed to operate the entire data center? Paul, you want to try that one?
yeah. So if we look at a 48-hour run, let's say you really you lost a grid, and you're just down to your batteries and hydrogen. As mentioned earlier, the batteries can only go so far, um, unless you've got a lot of batteries, and so the batteries can pick up the transients and load dumps, but it's all fuel cell and all hydrogen that's powering that the bulk of that 48-hour run. I mean, yeah, there's no way unless you have even more batteries on site.
Yeah. So Paul, this one's you too. What's the startup time for the backup system to come fully up to power?
Uh, really fast. Better than a diesel genset because again, we're using batteries here, right? And like Patrick was mentioning, this is like that sugar spike. It's like instantaneous. But with that being said, the fuel cell is it's no slouch. It's pretty good too. And, we did a lot of testing at the factory and even at the data center without any battery assistance. And um, I, I don't know if I will say too much more, but yeah, it's pretty good response.
Yeah. So the next one, I'm going to have to pass to Patrick offline. Are there systems where you can switch between storage tankers and continuous operation of fuel cells? And I'd say the answer is yes, but that's a very complicated question. So if you want more of an answer, please talk to Patrick on that. What's the cost of the project? We gave that on the first slide. So you can see that on the slide. Okay, is there any actions done to optimize power management regarding temperature? You might want to touch on that, Paul.
Temperature management for the fuel cell,
I would
just in
say
general. We've got a lot of
either
equipment on
one,
site.
ambient or the fuel cell, whichever one,
Yeah.
because it's not specific.
Yeah, we've got a lot of thermal management to do on site, both with the batteries and the fuel cell. But with regards to the fuel cell, and this is just our running of this unit for extended hours in the fall, and given Cheyenne's really brutal conditions where it was cold, and so I think we were okay in the thermal management side on the fuel cell side, and we had more cooling capacity than we needed. But if this was deployed somewhere else, I might have a different answer, but
Right, right. All right, so
but I think Ballard can do that too. I think maybe Patrick might have mentioned one of the other projects is in a pretty tropical place. So I would say that's the other extreme for thermal management. So this was an extreme where things got really cold, below freezing conditions.
yeah.
Yeah.
So
The challenge on tropical, just to maybe add a little bit to that, is the moist air. So in that case, the water rejection is extremely high. So you need to manage the water. I mean, it's pure water. There's nothing wrong with putting that back in nature, but it is considering that Cheyenne was opposite. We had to provide it, whereas in tropical countries, because you're taking in moist air, you have to exhaust that high moist air. So
okay, so I'm afraid I'm going to have to jump to the quick answered ones. Were there any surprises in operating the system versus a genset? Paul, you want to comment on that one?
Surprises. Well, this is a first of a kind, and so definitely more challenges to talk about. And uh, one of the things that we considered that could have been a possibility when we were doing a lot of the PHA and looking at the interactions between the different systems was a potential for nuisance alarms on the hydrogen side, especially with our battery containers, because you have concerns about battery off gassing and whatnot, and so maybe that was not entirely a surprise, but something that we had considered. But still, even when you think about things, when it happens to you, you still you still feel it, and so I think that's one of the things that we would take forward. And so for future sites and siting conditions, you might have to try to mitigate for potential nuisance alarms through design or changes with hardware.
Right. We've only got 6 more minutes, but So the system's dormant for long periods of time, right? Because it's only for backup. Is there any strategy to deal with the dormancy effect, Paul?
Yeah. So I guess to back up a bit, this was a demonstration, first of kind, using liquid hydrogen. And if this were deployed as is, the same way that we did this, you might have to think about boil off and what do you do with that. And in the past, Microsoft have suggested that, hey, maybe you can co-locate some of this infrastructure with other infrastructure, and you can use the boil off um, of the hydrogen for, say, generating power, or using that for refueling vehicles. So that's one way to manage it.
Sure.
Dormancy, I think the fuel cell needs to be run every so often, but I don't think that's a problem. Today for diesel gen sets at data centers, they exercise them, once a month, and so I assume we could follow the same schedule, or maybe even less, just depending on what the fuel cell needs in terms of how often it needs to run. But you can't just keep it there parked all the time. You have to run it every so often. But for diesel gen sets, about once a month, and the same could be said for a fuel cell.
Yep. So what was the grid forming asset? Was it a fuel cell inverter or a battery inverter?
The grid was formed by the Caterpillar PGS 1260s. That's our batteries and our inverter system in the 20-foot container. So the grid's formed by the Caterpillar assets, and then Ballard as a fuel cell joins the microgrid.
Mm. So what were the integration control challenges you experienced is there a need for more development?
Uh, there's always need for more development, but as part of this project, we realized that this was one of the challenges, and so we tried to work upfront, by obtaining, say, Ballard's controller even before the whole 40-foot container and all the pieces that Patrick was showing was built. We obtained that controller as Caterpillar, and we started interacting with it, and we did in-house testing a few different ways, on a bench, and at two different test cells, one at our own inverter lab, and then the other one with another microgrid type facility where we've got a few different assets running at the same time. And then when we did the factory acceptance test at Ballard, we brought our controls to Ballard side, and then we did everything, and then there's additional work to be done on site as well. So
Yeah.
yeah, a lot of work, and potentially more work to be done.
Yeah. So boil off, liquid hydrogen boil off. Was there a process used to recover it, or was it vented to the atmosphere?
In this case, it was just vented to the atmosphere, the boil off.
So a lot of people interested in the footprint, and is there a way to shrink the footprint because it does take up a lot of space? I don't know if you have the number right off on the total square meters or whatever of footprint it
Yeah,
took.
as mentioned earlier, maybe the size of a football field. And when we did the design work for this, we were using the older NFPA 2 requirements, and so we had 75 feet setbacks from the source valve to all the different air intakes, including the fuel cell air intake. So it's from the source valve, post vaporizer, it's about 75 feet to the fuel cell inlet, which is pretty close to the air intake of the fuel cell. To reduce the space that you need, and I think this would be Microsoft's preference. If they were here, they would say, yeah, I don't want that liquid hydrogen tank in my campus. Just send me a pipe and send me the hydrogen that way. And so you might reduce your footprint a lot by doing that. And then, at a data center, it's just your fuel cell, your cooling package, and balance of plant, and maybe batteries.
Okay, trying to go quick, but how many megawatt hours was in the energy storage system?
Yeah, so this is the PGS 1260. The 1260 stands for the maximum rating, and so it can do 1260 kilowatts for a really short burst, maybe uh, roughly, about 5 minutes, 5 to 10 minutes. But it can do 1 megawatt for 20 minutes. So that's about how much energy we have per container.
Right, right. All right. So, Paul, what about AC? AC out instead of DC? Why not DC out?
Why not DC out?
Yeah.
Yeah, no, that's a great question, and one that I ask myself as well, and ask others. Um, yeah, and I think there's been other projects where when they've just looked at DC out, but and maybe Patrick can speak to this because he's got a lot of experience in the electrical industry. But for whatever reason, we have all this convoluted, DC to AC and then AC back to DC. But yeah, I don't know, Patrick, if you got any more uh, wise insight into the world we live in.
Yeah, we'll go back to the battle of Edison versus Tesla. I think why we live on an AC grid today and not a DC grid. Um, so we definitely need. I mean, from the technology perspective, a fuel cell generates DC voltage. Then to discuss, hey, data centers could perhaps be more efficient if they ran on DC. Holistically, yeah, that's something that we could probably look at. For, at least from the fuel cell perspective, really, there's no. It's not complicated for us to fathom having a DC out just regulated through a DC-DC converter, and then feed some sort of DC common bus with the battery, and then you would be feeding whatever DC voltage to your loads. But we live in a world where everything operates off of AC, so you have to connect to the grid somehow, and
Yeah.
that's voltage.
Okay. Thanks, Patrick. I'm afraid we're out of time. Great questions, everybody. Appreciate them. And I guess we're just going to have to close this off. You can reach Patrick or Paul and ask your questions offline. Or if you'd like to hear more about this project, I urge you to consider going to the DOE annual merit review, May 6th, 7th, and 8th of this year in Northern Virginia. We'll also have a final report posted. We can get all the details, and so you can get more details and more questions that you have answered a little more thoroughly. So thanks, everybody. Special thanks to Paul Wang and Patrick Savoy. Thank you so much for helping us out and informing everybody on this project. So appreciate it. Thank you.
Thank you.
Thank you.